everyone. Okay, so just by quick way of intro, I'm the CTO, one of the founders of StorageOS, and I'm also the co-chair of the CNCF Storage SIG, so feel free to ask me lots of questions later on. So first off, Michael touched on this earlier. And we're going to talk about why cloud native storage and how this operates with composable storage and storage-aware applications. So we've determined there is no such thing as a stateless architecture. So all applications need to store state somewhere. So I'm going to talk a little bit about what we see in some of our end users in their journey to cloud native. So the first step tends to be to containerize. And we containerize applications to provide portability to the applications. Effectively, we're picking up the application and all of its dependencies and putting it into a container. And now we no longer have to manage the dependencies on a host-by-host basis. And then we move on to orchestration, where we have Kubernetes, which does a fantastic job at automating and scaling and managing the deployment of all of your applications. And Kubernetes effectively abstracts away your infrastructure. With Kubernetes, you can now make your application declarative and composable. And what does that mean? It means we can say, my application needs this type of CPU, this type of memory, this type of network. And Kubernetes plays an amazing game of Tetris with your applications and fits it into the appropriate infrastructure. But of course, as we said, no application is stateless, and you eventually get to the point where you want to move your stateful workloads into Kubernetes too. So there are a number of options using existing storage or software-defined storage or even cloud services. And software-defined storage and cloud-native storage gives you the capability of now taking your declarative functionality that you've used with your orchestrated workloads and move it onto yours and give you that functionality in your stateful apps too. So you now have the ability to do things like self-service functionality and use the cloud-native storage to abstract away the storage functions of your infrastructure too. So when we started working on cloud-native storage, we put together a number of principles which we use to define what a cloud-native storage system needs to look like. And these are kind of important because they apply to any cloud-native storage environment, whether it's software-based, hardware-based, or cloud services. So the first and most important thing is that storage needs to become application-centric, right? So we're moving away from an era when we're providing storage to individual nodes or to hypervisors or operating systems. And we're now presenting storage, and storage is getting consumed by the applications directly. So as applications move around within your Kubernetes environment, they're consumed, the storage needs to follow them as they move around. We talked about the applications being containerized. And by making the applications containerized and putting all the dependencies of an app into a container, the application becomes platform agnostic. So of course, the storage system should also be platform agnostic and should be able to run anywhere. So you want the capability of the same levels of storage abstraction, whether you're running in the cloud or on-prem. And in just the same way as you specify things like CPU, memory, and network ports for your application, you also should be able to specify what your application needs in terms of storage requirements and the types of attributes of that storage too, and the types of services that it requires. Now, of course, for an application for a storage system to be declarative, it needs to be API-driven, and it needs to have a rich set of APIs that can integrate natively with the orchestrator. And this provides the ability to do things like dynamic provisioning and the ability for developers to self-service their applications. Of course, we're often running in multi-tenanted clusters, and those clusters are often running in the cloud. So cloud native storage needs to be natively secure. It needs to have some of these features baked in from the ground up. So things like supporting the namespaces and RBAC capabilities in Kubernetes, as well as providing services like inline encryption to protect the data in co-located or managed environments. Now, I put this in, and I always get a few looks because Agile is obviously quite cliche, right? But what I'm trying to say here is, in a Kubernetes environment, we have a lot of moving parts, right? Kubernetes does a great job at managing where your applications need to move. But it's also there to automate and to scale your applications and to heal your applications when something breaks. So in a Kubernetes environment, nodes come and go. You may choose to upgrade your nodes from a software point of view. You may choose to upgrade your nodes from a hardware point of view. And therefore, the storage system needs to be able to cope with all of those moving parts and maintain access to the data as those changes happen. And finally, the last 2 points kind of fit into this agility. So when you're looking at an environment which has all of these moving parts, the storage system needs to be able to provide deterministic performance and provide consistency of availability while all of these changes are happening. So as nodes, for example, fail and data needs to be recovered, you need to be able to have that same deterministic performance, and you need to still have predictable access to your data. So we're going to talk a little bit about how Kubernetes manages storage persistence. In the first place, we used to create a pool of individual volumes, right? So this might be, for example, statically provisioned disks or statically provisioned cloud services into your Kubernetes cluster. And a developer in the YAML for their pod used to be able to claim one of those physical volumes. And that claim would then get mounted and bound within the namespace of the pod. But of course, this is very, very static, and it's not very compatible with a lot of the things we just talked about in terms of being application-centric, but also providing the dynamic provisioning capability. So as we move on into the realms of dynamic provisioning. And in dynamic provisioning, we have the concept of a storage class. And a storage class refers to a storage provider. That storage provider is typically nowadays accessed through a CSI driver. So that storage, the storage class has a number of attributes and a pointer to the CSI driver. And it allows you to abstract away how you access the storage, because now a developer can claim a persistent volume from a storage class. The Kubernetes will use the CSI driver to dynamically provision a persistent volume from that storage class, which then gets mounted into the pod. So we're now going to talk a little bit about storage-aware application placement and why this is important. So in a typical scenario, you have an application developer that defines what they require out of their pod or their application. That goes to the Kubernetes scheduler. And the Kubernetes scheduler, as we said, does a great job at playing Tetris with all of the pods and fits in it's the best job of fitting in those pods to the available infrastructure within the cluster. But of course, we have Kubernetes can be extended with the ability of putting in a custom scheduler. And a Kubernetes custom scheduler allows you to manage additional functionality and provides additional prioritization to the Kubernetes scheduler to allow the pod placement based on more application-aware facilities. So for example, using a storage scheduler that interacts with Kubernetes, if the pod defines the scheduler to use, then Kubernetes will talk to the storage scheduler and send the storage scheduler a list of nodes which are available for placement on the pods. The storage scheduler then filters that list based on a set of criteria and prioritizes that list and provides a scored set of node information back to the Kubernetes scheduler, which then uses that scoring mechanism to optimize the pod placement. Now, this functionality works well, but it does mean that each pod needs to be customized with an individual storage scheduler, which kind of detracts a little bit from some of the benefits that you have with having, say, your abstraction with a CSI driver or a storage class, for example. So the newer way of doing this is to use an admission controller. So an admission controller is effectively an API webhook which is referenced by the Kubernetes scheduler after things like authorization take place. And that admission controller can do a number of things. It can validate your pod definition, but in this case, what we're looking to the admission controller to do is to mutate the pod definition, to automatically add in the storage scheduler definition. So now you no longer have to define a customized storage scheduler. You can use the admission controller will automatically add in the storage scheduler definition for that pod placement. So what does that mean? It effectively means that we now can schedule pods local to where the storage is positioned. And why is that important? Well, there are a number of different applications which benefit from data locality or better positioning of pods and data sets. The obvious use cases are things like databases, for example, and this applies to both SQL-based databases as well as NoSQL-based databases like Cassandra or Mongo, for example, where specific locality of the database instance and the actual running pod is really important to achieve the deterministic latency that we talked about. Again, things like stream processing, like Kafka, for example, where you have, and equally things like message queues, like RabbitMQ or things like that, where you have, where you either have lots of little events that need to be processed or large analytics, which stream large sequential amounts of data. If you want the throughput and you want the deterministic latency, again, the data locality is quite important. Similarly, things like analytics, like Elasticsearch, but also things like CI/CD. And in the case of CI/CD, what we're looking to do there is you're typically going to have an environment where potentially hundreds or thousands of pods are spun up in these environments. And each of those pods needs access to the data dynamically. So, you know, Michael talked about the number of changes that are happening in a cloud-native storage environment, which is typically, you know, thousands potentially per hour. And that's exactly the type of environment where data locality benefits here too. And of course, last but not least, things like VMs running in Kubernetes. And you go, okay, VMs in Kubernetes? Yes. So with projects, there are a number of projects now, like the KubeVirt project, which was recently adopted as a sandbox project in the CNCF, which actually allows you to run VMs as workloads within Kubernetes. And this functionality provides you the ability to move some applications that can't be containerized for some reason. So for example, a typical use case might be telco-based applications that are dependent on, for example, specific Linux kernel drivers or something like that. So the best way to show the impact of storage aware locality is to actually run some sort of benchmark or something that where you can actually quantify some of these numbers. So in this case, I use pgbench, which is used to benchmark Postgres against a remote placement and a localized placement. And for the purposes of this benchmark, I used a managed Kubernetes service in DigitalOcean and used some of the smallest nodes possible. The idea being that we wanted to test the effects of the network and the storage rather than, you know, speed things up artificially through large caches or large amounts of memory. So with remote placement, we saw an average latency of 6.5 milliseconds. With localized placement, that latency dropped to 2.6 milliseconds. And of course, the number of transactions per second in this case is directly proportional to the latency of your applications. So by having your pod closer to your data and reducing the latency, we got a more than 2x increase in the number of transactions per second. And yes, this is a fairly small PG bench test with just 1 million rows, but it's indicative of the type of benefits that you can typically expect. So now I'm going to hand off to Ferran. Ferran is one of our product reliability engineers, who's obviously way more photogenic than I am, and he's going to give a little demo of storage-aware application placement in practice, assuming the Wi-Fi works.
Yeah, it's going to work. First of all, I'm going to start with a couple of clusters, Rancher server using a GKE clusters. Could be in Amazon, it could be everywhere, anywhere, but just for context. So let's go to command line. Let's verify that the network is all good. I'm going to use K instead of kubectl, but I guess we are all familiar. So first of all, StorageOS is installing this 3-node cluster. One daemon set pod per node. We're going to aggregate the capacity in there to provision a file system or a block device to the containers. So the first thing I'm going to use is a Jenkins manifest, which pretty much is an example of a CI/CD application, but for the purpose is, okay, very often applications such as databases mean that we need the lowest performance possible. But in an environment where everything is orchestrated and we can have hundreds of nodes, having an application-centric deployment becomes fundamental. So I'm just going to create this application and show you a bit what the Jenkins look like. Right. So what did I do? Using a stateful set. If you're not completely familiar with the concept of a stateful set, don't worry too much. And I know that the light is a bit dim. So again, don't worry too much. It's in GitHub. It's completely available. So if you need to check it out properly, it's completely public. But pretty much it's like a deployment, but for the stateful applications that have, that ensure some parameters that stateful applications need. Essentially, what we want to see here is this controller and how the data is provisioned. So first of all, being application-centric means we want a controller that ensures that when we create an application, a pod, it creates its own volume. It creates its own persistent volume claim. And by using StorageOS in this case, just for the demonstration, we're using this storage class to talk to an external provisioner that will be able to fulfill everything that Kubernetes needs. So this home is the Jenkins home directory that is mounted into, obviously, the Jenkins home. Nothing out of the box. Cool. So what happened, we deploy only one replica, is we have a Jenkins starting, good, and we have a persistent volume claim. And let me make this here. So we have a persistent volume claim that match with the pod, right? So every time we scale this deployment, or this stateful set, we will have one new volume per, let's say, Jenkins slave or the primary, right? And this is quite trivial and quite obvious. So now I'm going to use the StorageOS UI. Let's pour forward into the cluster that the network was prepared. So this was working. So what that means, let me go to the UI. So we can see one volume, right? And hopefully you can see this, right? So what we can see here right away is that we have provisioned, let me make this bigger. We have provisioned this volume that is dynamically provisioned. This is application-centric. An application needs capacity. The storage operative software needs to give that capacity. What happened in the end is you can see that that's running in node B76W. That's where the data is stored. And this is a replicated volume. But actually, this is being mounted. So the pod is running in node R44C. So you don't see, pretty much, this node here is the different from there. Meaning, we're accessing through a network, this data through a network. And this is OK. So for operability, this is all right. But what happens when we really, really need a lot of pods? So I'm going to scale this stateful set and say, I want 7 instances of this application running. So what happens is that we deploy automatically more persistent volume claims. So you cannot see shit. Right? So now we have the 7 persistent volume claims being provisioned. And the pods are starting and mounting them. And we start having a farm of Jenkins servers. All right. What has happened is that as soon as we go to the StorageOS UI, we can see that those volumes may or may not be, again, different nodes placed together. And that means that we have network amplification. So yeah, we are dynamically provision everything, but we can do better. We can do way better than this. So when we say application-centric is, OK, we want the storage system to talk to the application scheduler, right? So let's use the second cluster that I'm actually using the newest scheduler that we have implemented, so an extension of the Kubernetes scheduler that is aware of where the storage is placed. So let's use the second cluster. So again, this is 4-node cluster. So let me, it's bigger. So just to make sure that we know where we are. The other one was 3 nodes. This is 4 nodes. So we know that it's actually a different cluster. So you don't have to take my word for it. And actually, one thing, before I forget, one thing that is important here is this. This is the StorageOS scheduler pod, which is an extension of a Kubernetes scheduler, right? So when we have to provision a volume, it will provision, and then Kubernetes will know where to put the application. Oh, sorry. Jenkins. So again, in the second cluster, we have the persistent volume claim created. OK. We have the pod starting, hopefully. OK. So now let's connect to the second cluster. Good. So if you're not familiar with this, don't worry too much. It's just accessing localhost to, tunnel into the cluster. So here, just make sure we have one volume. Happens to be that they are in the same node. So where the primary volume, where the data is actually being read from and write to, is in the same node where the application is running. And again, OK, this is fine, and we have to do nothing. It's just enabled by default. This is great. Again, what happens when we scale this? And it's 30 seconds, and you're free for a coffee. Right? So get pods, get PVCs. Again, you can see a bunch of them. And now we can start seeing that, hey, these volumes are placed in the same nodes. So application-centric, in the end, means this, that by default, something that is smart enough that has behavior can give you the best performance you can get in a 50-node cluster. And you start mitigating all the network traffic and all the amplification that you get out of using the network. Right? So pretty much this is application-centric, and you're free for a coffee now.
OK. Thanks, everyone.
Okay.